Here I am. Writing scientific notation, beginning with that. Of course, we must open it twice. And there. Write each number in scientific notation. So what you do is you count the number of zeros that you can see. Oh, what? I have to open it a third time? That's never happened before. Oh, I see. Okay. Yes, as I was saying, you have to count the number of zeros that you can see. So I can see 6 of them. So I write times 10 to the minus 6 on the end. And what do I write at the start? I then write the non-zero digits that actually make up the content of the number. So I write 6 right there at the start. That's when you have a teeny tiny number that is less than 0. As for a number that is bigger than 0, you've got to count how many jumps you have to make to get between the first two non-zero digits. And in this case, it happens to be 6 as well. So this is 5.4 times 10 to the 6. But let's make sure that makes sense. Let's make sure that makes sense. 1 million is 10 to the 6 because it's 6 copies of 10 all multiplied together. And this number right here is 5,400,000. Sounds quite reasonable. That would just be 5.4 times bigger than the above, which is what it is. So let's proceed now with the rest. And how many are there to do? 32. Okay, commence. Here, this is in a sort of pseudo-scientific notation. So we're going to make this 10 times smaller and this 10 times bigger. To make 10 to the 3 10 times bigger, it becomes 10 to the 4, just like that. Nine times 10 to the negative 7. All right. Make this 10 times bigger. Make this 10 times smaller. This one 10 times smaller. And so this one 10 times bigger. Ten times bigger, 10 times smaller. And checking those first few, checking and making sure that they are correct. Good. 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 Correct. 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 Next up, write each number in standard notation. Not scientific notation, but standard notation. like as an ordinary number. So this we are dividing by 10, so it becomes 0.09. We introduce an extra 0 in the zeros that we can see. Here we can't see any zeros, so the only place for it to go is at the front before the 2, so it'll be 0.2. But always make sure that in the back of your mind you know what this means. This means 2 times 1/10, which is a tenth of 2, which is 0.2. This here, instantly interpret it as 250, as 200,000, 200,000. And here, multiply it by 100 to get 80,400. By 10,000 to get 26,600. Divide by 100 to get 0.015. And now by 10 to get 0.775. And here, this will be times 10 million. 10 million. So it will be 83 million. This by 10 million is 95 million. And this is not 10 million, but 17,100,000. Divide by 1,000, so introduce an extra 3 zeros, just like that, and times by 100 to get 3,800. And now divide by 100,000. Introduce 5 more zeros than what we can see. So 0.00075. And here, this will just be 4. Times this now by 100,000. So multiplied by 100, it's 840. So it'll be 840,000. And now, finally, at last, just introduce 5 more zeros. There. And check. Check everything that you've written. Make sure that it's correct. True. Gotcha. And it's all good. It's all good. Next up, operations with scientific notation. Thus we begin. Thus we commence. We're to write each answer in scientific notation. But how do you do this? How do you do this? This number is multiplied by this number. So there is a multiplication symbol between these brackets. And we don't need brackets if we're multiplying a bunch of things together. So really, this is 1.08 times that times 9.3 times that. And then we can move everything to the front, the 9.3 and the 1.08. And move the 10 to the minus 3 and 10 to the minus 3 to the back. Just like that. Now we have 9.3 times 1.08, which you should be able to do, so do it. $10.04. So we get 10.04 times 10 to the minus 6. But this is not allowed because this is above 10. So make it 10 times smaller and make this one 10 times bigger. 1.004 times 10 to the minus 5. How about that? Okay, same thing for this. The little bits at the front are called the mantissas. The mantissas. So do 2 times 8.1. 2 times 8.1 to get 16.2. And then do 10 to the minus 4 times 10 to the minus 1 to get 10 to the minus 5. But you must correct it because this is not in scientific notation. Not right now. That's above 10. So make the front part 10 times smaller and make the back part 10 times bigger. So it becomes 10 to the minus 4, like that. And continue for these 4. Okay, try. 4 times 2.32, what's that? 9.28. 3.48 times 9.8. What is that? $34104. And then, there we go. And correct it. 10 times smaller, 10 times bigger. Good. 7.1 times 6.7. 47.57 times 10 to the minus 11 and correct it. 6 times 9.91. 5.946. No, 54.946. No, 54.946. Oh, I'm getting that mixed up, aren't I? Try again. 59.46. 59.46. That's better. Times 10 to the 3. Okay, correct it. 10 times smaller, 10 times bigger. Okay, what now? What now? Well, just like fraction multiplication, which works like this, I can split this up into 7.1 over 8.2 times 10 to the 6 over 10 to the 1. That part I can do because it's 10 to the 6 take 1 is 5. But 7.1 divided by 8.2, I guess I can't do that. I don't know. So I have to resort to the calculator. Okay, so it's 0. Should I be? Well, let's think. I have two significant figures there and there. So my reply should be that accurate as well. So I say 0.87, but then I must make it scientific notation. So 8.7, 10 times bigger, 10 to the 4, 10 times smaller. Okay, let's do it. 5.4 divided by 3.4 is 1.59. Minus 1 minus 1 is minus 2. And there you go. Now, what about this one? 4 divided by 3.63. So I'll just give them 3 figures of accuracy. Okay, so 1.10 times 10 to the 4 minus 4 is 8. And here, (0.974) minus 5 minus 6 is 1. Fix it 10 times bigger, 10 times smaller, and continue. Divide that by 5. That I can do. 1.684. And there we go. I cannot do that division without a lot of time. So what should I say here? Well, it should be to 2 figures, so 1.1 technically. But I'm going to say 1.06 because it's very close. It's like 1.059. Anyhow, that's fine. Okay, now what to do about this? What to do about this? That 4 will be applied to the 8.9 and to the 10 to the 5. You will have to raise 8.9 to the power of 4 and 10 to the 5 to the power of 4. Both of them. So 10 to the 5 to the 4, that would be 10 to the 20. And 8.9 to the 4 is approximately 9 to the 4, which is approximately 6,561. But that's not good enough. You have to actually figure it out. Okay. 6274. But how accurate should I make it? Well, we'll just do 4. Should I do it that accurate? Well, let's just see. And you know, I really don't like it when we have approximations and we don't acknowledge that they are approximations. So these are all wrong, all wrong. That needs to be corrected. There. See? Much better. Because it's true. Likewise here and here. Now here, it became an approximation right now. Okay, so then I proceed from that, and it's no longer an approximation because I'm saying that is in fact equal to this. So I'm going to make it 1,000 times smaller, and this one 1,000 times bigger, just like that. But what to do for the 14th one? Well, same logic, right? 4 to the minus 6 and 10 to the minus 5 to the minus 6, which is 10 to the 30. Now, what is 4 to the minus 6? Well, notice that 1 over 4 is 0.25. 1 over 16 is 0.0625. And 1 over 64 is 0.01565. So you're multiplying by 25 every single time. So potentially I could get there, actually, if only I knew 5 to the power of 12. 5, 25, 125, 625, 3,125, 15,625, 78,125, 390,625, and I run out. So, okay, so we'll just do 5 to the 12, see what that looks like. And we get that. Yeah, I'm going to write this down. And then we get something in scientific notation as well. I'm going to do all the places. That's to the -4, and that's to the 30. So now we can just conveniently add them. 44140,625. Because I like accuracy. This one, I can do it. 216 times 10 to the -15. 100 times smaller, 100 times bigger. I can't do this. 6.3 to the -6 is, okay, approximate sign, please. 1.599. Let's just say 1.6. Times 10 to the -5, and then times 10 to the -12. And that is the same as this. Continue. 5.21 squared is what? 27.1441. And this, and divide that by 10, and times that by 10, and there it is. 2.4 to the power of 4. What's that? Well, that would be 5.76 squared, which is 331,776. And there's a decimal point right there. And that's times 10 to the minus 20. And now, like that. 10 times smaller, 10 times bigger. Next, I don't know how accurate all of these are, but we'll see. We will see. 3 divided by 8 is 0.375. And this is that 10 times bigger, 10 times smaller. Well, 4.1 divided by 1.28. That's the same as dividing by 2 7 times in a row, something like that. But for the sake of this, there. And now divide that by 5. So 0.382. And that will be that. Bigger, smaller. I cannot do that calculation. Okay, so 0.306 and to the minus 12 and fix it. Bigger, smaller. There. Okay, this one dividing by 111. That has specialness to it, but can I get acquainted with that specialness right now? So 1.617-ish. Approximation sign, please. Times 10 to the minus 3. 8.8 to the minus 5 about 1.90. Times 10 to the minus 5. And then that is times 10 to the minus 25, actually. Understood. So 6 divided by 8.08 is that. Approximately equal to sign 0.743 times 10 to the minus 1. 10 times bigger, 10 times smaller. Continue. 3.5 times 9, I can do that. 31.5. And I can do this. And that would be smaller, bigger, like that. And 8.8 times 2.25 compute. $19.8 and add them, and it's that. 1.18 divided by 3 is 39. But something's after that. But hold on. Okay, 0.393 and then the recurring 3. Like that. And now what? This. And now fix. 10 times bigger, 10 times smaller. And we get that. Now check. Everything must be checked. Forever. Literally check everything. And if it's wrong, it's wrong. And that's all there is to it. It doesn't matter. Correct. 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 You know, okay. Okay, they decided on 4 sig figs. I see. But we agree. Gotcha. Next. Inaccurate. Inaccurate. That's better. So fix. Wrong. That is an approximate sign. And that is an equal sign. Better fixed. Inaccurate. That was not... No, that's not inaccurate. That's incomplete. Incomplete. Complete. Smaller and bigger and fixed. And that is good. So it's all good. So just a moment. Get some water before doing the next. Next comes addition and subtraction with scientific notation. Only 14 tasks to do. So probably I won't be able to do... No. Try and do as many as you can without calculator assistance. 3.1 at 7 at 4.3. There. So 670 in standard notation, which is 6.7 times 10 to the 2 in scientific notation. $24,000 plus 5,570 in standard notation. So 29570 in standard notation. Decimal point there, times 10 to the 4 in scientific notation. Now, that plus that yields what? 0.0516, which is 5.16 times 10 to the minus 2. This is 25, and this is 61,400. Put them together and you get 61,425, which is 6.1425 times 10 to the 4 in scientific notation. This is 0.7, and this is 0.0000064. So put them together, and what do you get? 7.00064 times what exactly? Times 10 to the minus 1. This is 0.005, and this is 0.0000033, like that. So what do we get? Well, we get 5 right there, 0.0033, and then it's all times 10 to the minus 3. And here, 0.8 plus 6,900, which becomes 6.9008 times 10 cubed, like that. And now subtraction. So this is 139,000. This is 400. And that gives 138,600, which is 1.386 times 10 to the 5. 0.274 minus 0.000653, which gives 0.273347. So we write 2.73347 times 10 to the minus 1. Next, 814,000 minus 780, giving 813,220, which becomes this with the decimal point right there. And 6,360 minus 0.58. So 6,359.42, which is 6.35942 times 10 to the 3. And now 0.51 plus 3,800, which is 3,800.51, which is 3.80051 times 10 cubed, like that. Next, 0.059 minus 78, which is negative 77.941. Is it not? So negative 77.941 times hold on, that's not right. This times 10 to the 1. And check everything. Check everything. Valid. Correct. And next, discrete exponential growth and decay. Okay, only 4 tasks. Not very bad at all. An employee receives a 2% raise once per year. If the employee's initial salary is $60,000, what would the employee's salary be after 9 years? The answer is 60,000 multiplied by 1.02 to the power of 9 to the nearest hundredth. Which is $71,705.55. And of course, we have the approximation sign there because that's accurate. And now we use the graph just merely out of courtesy, I guess. So it starts there. And by year 9, it finishes around about there-ish. So it'll be a nice, but not linear, increase like that. And somewhat more after that. Anyway, a new social media site is increasing its user base by approximately 6% per month. If the site currently has 21,740 users, what will the approximate user base be 8 months from now? The answer is 21,740 times 1.06 to the 8 to the nearest whole number, because that's what makes sense for users, counting users. So we say 21740 times 1.0. And we get 34,650. And here it is. And here it is. And that'll be an increase. Something like that. It'll just be going up quite a bit. Anyway, a robot vacuum cleans a dirty floor using multiple passes. During each pass, 22% of the dirt is removed. If the floor initially has 530 milliliters of dirt, how much dirt will remain after 10 passes? So it will be 530.0 multiplied by 0.78 to the power of 10 to the nearest tenth. Which is 44.2. That many milliliters of dirt. So we say that, and we write down that, and we have this decay function here. Okay. A country pledges to reduce its annual CO2 emissions by 3% per year. If the emissions in 2022 are 3,030 MTs, metric megatons, what are the maximum allowable emissions in the year 2028? So it would be 3,030 multiplied by 0.97 to the power of 6 to the nearest whole number. So we type that in. And we obtain 2,524 metric megatons. And now we graph it. There. And this is by year 6. So it should be there-ish. Gradually going down now. And that's all good. And now we check. Accurate. Okay, they want the units. I guess I must be explicit about that. All right. Correct. All of it correct. And that finishes this. So be well, be well.